So let's talk about the water droplet one a little bit. I'm going to draw a bit of a picture. And if nothing else, I just want to frame what's happening. So I need a ground. And I need a building. And so now we need some droplets. So there's a couple things here that I think bear discussion. Water droplet 1 is just about to hit the ground, right as water droplet 5 is being released. So the one near the ground is 1, and the one at the top of the building is 5. Can you guys see that okay? Hard to see on this board? Because of the shine, or because of this thing? Yeah. Sorry. Can't take this thing down. Maybe they'll install my projector someday. It was November when it was ordered. So they promised they're working on it. I have the kit and the tools just sitting in my stockroom. I can just do it. But at this point, I might get fired if I do. So consider that droplet 2 is probably right about here. Droplet 3 probably here, and droplet 4 here. Actually, 4 is probably up a little higher. You know, if we want to be really specific, they should be spaced in such a way that they suggest a squared relationship. Now, we are given this distance, right? The distance of the window. So you are familiar with this question because we had the window problem. A little different, but the window problem. And that's really all we've been given. So in my version of the problem, this is 1.2 meters. But everybody probably had a slightly different amount here. So you'll have to work that into the problem yourself. We do know that it's even increments of time between all the droplets. I called that increment capital T. So it takes 2t for the droplet to reach the top of the window, 3t for the droplet to reach the bottom of the window, and 4t for a droplet to go from the top of the building all the way to the ground. If we can figure out t, we can figure out how tall the building is. So that's what I want to do. I want to figure out t. And I have information I can use to figure out what t is. Couple different things. Now, the way I went about solving the problem was to consider that ultimately the only way I'm going to be able to solve the problem is if I can find some things about the falling of the drop that I can use to bring to bear on a problem. And one of the things I thought is I could consider what happens to go from the top of the building to the top of the window. And the reason I'm using the top of the building is when I think of my motion variables, I always try to find ways to consider which variables I can make 0 or which variables do I already know. For example, I already know that the acceleration is 10 meters per second squared. That's a motion variable that I know. All I need is 3 variables. I know that if I deal with the top of the building, the initial velocity of the droplet is 0. Based on what I've drawn so far, the time is 2t. But that's all I know. I mean, I could say it fell a distance d if you'd like, but I don't know that either. Now, I'm interested in the whole building, so I could consider looking at the top of the building to the ground. I don't think there's any information here that's going to help, though. I don't think I can figure this out directly. I will know that the top of the building still has an initial velocity of 0. The next velocity, I don't know how fast it goes when it reaches the ground, but it has an acceleration of 10 meters per second squared. And the time to reach the ground is 4t, but that's all I know. So I don't know anything else. I don't know how tall the building is. So delta x is an unknown. On the other hand, I could consider the fact that there is a similarity and one more piece of information I haven't used. If I consider the top of the building to the bottom of the window, then I would start with a v naught of 0. I would not have the final velocity, but the acceleration would be 10 meters per second squared. And the time would be 3t, but now delta x would be d plus 1.2. That suggests that if I use this information and this information, I should be able to create two relationships that have a shared set of variables. This one would be d equals 1/2 a t squared plus 0t. Yep. I can't hear you.
It's not really showing up on the projector.
Okay. That's probably a better way to go. I can't see it. Can you see that?
That's much better.
So red's, yeah, I think the red emitter on that projector is actually going. It uses a prism and 4 LCDs, and I think the red LCD is just on its last legs. The other side is going to be d plus 1.2 equals 1/2 a t squared plus 0 times t. Now, my big head's in the way. No, it's not. Now, this gives you a way of solving for t, but then you could use that to figure out the height of the building. Now, what Max decided to do, which is just as effective, he recognized that he could figure out this velocity, or at least, no, not that velocity. He could figure out the top of the window velocity.
Yeah.
He could get an expression for the top of the window velocity as being v equals 10 times 2t. And what did you do with that information?
Well, first I wrote it as 20t, and then I put it into the 1/2 at squared plus the initial velocity times t equals delta x equation, but I just wrote it for the distance of 1.2 meters.
Okay, so instead he went to a different set of motion variables that describe the fall portion from the top of the window to the bottom of the window. So his V naught became 10 times 2t. His final velocity, I would assume then is, did you put 10 times 3t?
We didn't worry about it.
You didn't worry about it, so A is 10. And t was t. And delta x is 1.2. This will work too. This is still doing a simultaneous solution. He used originally, and although he's not showing this or not saying this, he's using v equals at plus v naught for one of the relationships, the fall of the droplet to the top of the window, and then substituting it in for the initial velocity for this fall. It doesn't require a simultaneous solution, but it's still substitution. So if you think that's easier, that's great. Nothing wrong with any of that. You would then make one motion equation out of all this. The only unknown is t, and you can solve it for t. Good job, Max. Now, in order to back up to where he's asking, I'm going to get rid of some of the distracting information that's here. what Max is suggesting we do, which is different. So we're starting from scratch as if we have not considered the problem the way I was talking about it, okay? He's saying, what if we only look at the fall of the rock, the droplet, from the top of the window to the bottom of the window? Although we don't have enough information straight away to do that, it is possible to get an expression for how fast the droplet is going based on other quantities we've been given. Because we do know from the top of the building to the top of the window, the initial velocity was 0, the acceleration was 10 meters per second squared. The final velocity is not known. The time, though, is 2t. If I stop thinking about displacement, I could get an expression for the final velocity. And this expression has just t in it. So, with that, I could use that as my initial velocity for the time period when it goes from the top of the window to the bottom of the window. This will not require a simultaneous solution. It will require substitution. And that's about all I want to say on the matter.